In this section, we will concentrate on Bayesian computation technique, a path-breaking work in 1990. Before that, the classical people were in driver's seat, in the sense that when the prior and the likelihood are combined together, in many situations Bayesian people are not able to find the posterior distribution analytically. So then one was looking for the computational technique by which at least you can have some idea about the posterior distribution. So in 1990, Gelfand and Smith, they developed this Bayesian computing technique, in the sense that using the classical Metropolis-Hastings algorithm, they considered the Bayesian computation technique where the posterior distribution can be derived very easily. So what we will do is that we will see in subsequent stages that the more general technique, the Metropolis-Hastings algorithm, and then from there how these simplified techniques can be considered to resolve many situations where one is not able to find the posterior distribution very easily. All right. See, this is the third section where really the magic comes. I am sure that you will get inspired by these computational techniques, because as I said that before 1990, the classical people were in driver's seat. The reason that in many cases the posterior distribution are not really manageable. Let me just tell you one situation, like when you have the data coming from some simple normal distribution and with say even variance to be known, and then if you take the prior for the mean parameter to be Cauchy distribution, then combining the likelihood for based on n observations for the normal distributions with common mean mu and variance to be known, and also with the Cauchy prior, you see that the posterior distribution is not really manageable. It is really analytically one cannot cope with that, how to get the posterior in nice form. So, what other way out came up in 1990, Gelfand and Smith, they jointly published couple of papers motivated by the work of Jeman and Jeman in IEEE transactions, where these Gelfand and Smith wanted to show that even if the posterior distribution is not manageable, is not tractable, one can possibly generate observations from these distributions, and if you are able to generate 10,000 or 50,000 or 1,00,000 observations from the distribution, you are really comfortable with the posterior distribution. You can plot it, can find the posterior means, population, posterior variance, then posterior quantiles, posterior medians, everything you are able to compute. So, this is basically what we are going to learn, that how the Monte Carlo Markov chain technique leads to the computation or generation of observations from the posterior distribution of interest. All right. Two main approaches are there. One is independent sampling and other is iterative sampling. So, suppose you have observations drawn theta 1, theta 2, theta m from some posterior distribution. If you are able to draw these observations nicely and they are all independent sampling, then nothing wrong. One can always use the Monte Carlo or whatever based on the generated observations, one can draw the inference about the posterior mean and posterior variance and other parameters. And in iterative sampling, what is happening is that essentially we are going to follow this part, second part, where given the earlier stage sample observation, how efficiently we can generate the next stage sample observations from the posterior distribution of interest. This starts from the Markov chain Monte Carlo concept. Now, what is a Markov chain? Markov chain is that probability xn plus 1 equal to j given x naught equal to I naught, so on, xn equal to In is essentially probability xn plus 1 equal to j given xn equal to In. So, what it stands? That n plus 1 step only depends on nth step. So, this is the transition probability, transition from the xn to xn plus 1, where the state space are the values I naught, I1, I2, In, all these values belong to the state space. Now, the transition distribution and stationary distribution of Markov chain. A Markov chain is constructed by specifying a transition probability. So, we need to specify transition probability appropriately, so that this Markov chain leads to the ultimately the stationary distribution of interest, and the stationary distribution is the posterior distribution. So, this Markov chain, the first stage, where when you go for specifying the transition probability, the dancing steps occur, up and down, go and back and forth, this goes. So, ultimately the dancing steps occur, and then this Markov chain, which must ensure aperiodicity and irreducibility, has a stationary distribution. Just the analytical property can be proved for there. We skip that here, and the idea is that the Markov chain is appropriately constructed with this aperiodicity and irreducibility property, so that it goes to the stationary distribution of interest, which is the posterior density. You see, this is a situation diagrammatically I can show you that the Markov chain between, when goes on, ultimately, actually in the gift sampling this will be more clear. The first, there are three graphs, the first step is that based on the small number of observations, it starts dancing, and then after that it goes this way and that, this way and that. Then the more you have observations, it goes more or less in a stable pattern. So, this is how the stationarity occurs in the third graph, where from here there is no idea basically with the small number of observations, but the second stage it goes this way and that, from this value to other value and that, and then randomly when you have so many observations, then the generated observations follow stable distribution, stationary distribution, stationary pattern I should say. So, this is the basic idea of the sample generation part actually. We try to demonstrate that through the algorithm. Now, Metropolis long back, without knowing the Bayesian concept, developed the algorithm, which is very useful, and in fact the modern algorithm is based on Metropolis algorithm. He said that you start with theta naught, an initial value, then at the kth step draw theta star from the jumping distribution from theta t minus 1, you are going to tth step taking some value theta star. So, this is the proposal distribution or jumping distribution. Anyway, so the jumping distribution is jt theta star given theta t minus 1, and he assumed that this jumping distribution to be symmetric, in the sense that jt theta a given theta b is same as jt theta b given theta a. So, this should be theta a instead of theta b, this should be theta a, okay? And then calculate the importance ratio R, which is p theta star given y over p theta t minus 1 given y. So you know that the posterior density form, but you do not know the constant or anyway how to get it generated. Think of the example I mentioned, that merging the normal likelihood with the Cauchy distribution or Cauchy prior. You see that the form is known to me, but I don't know that ultimately what is the form of the distribution, so that I can, because the constant part is not known to me. So the form of the distribution is the product of likelihood and the prior. So one can always have the posterior density is proportional to that. Now when I calculate the importance ratio R, the constant part goes out, because cancels out, because the numerator and denominator the constant part remains, so they get cancelled. Only you have the product of the likelihood and the Cauchy prior, this kind of thing. All right. So that theta star is a new value, and previous step we have the theta t minus 1. So we set theta t to be theta star with probability R. If the jump increases, the posterior density, set theta t equal to theta star. Very simple. You know that when I say that the jump increases means, you know, when R greater than 1, that means p theta star given y here is greater than p theta t minus 1 given y. So that in that case the chance is, I mean, strongly you accept the observation that you have generated now theta star. Okay. So as I said, that if the jump increases the posterior density, set theta t equal to theta star. If the jump decreases the posterior density, set theta t equal to theta t minus 1, the previous one, with probability R, and set theta t equal to theta t minus 1 otherwise. It should be theta star, theta t equal to theta star with probability R, and set theta t equal to theta t minus 1 otherwise. There is a code for that. Essentially this code gives you that how to generate observations from the bivariate normal. We know that we can do that always, taking help of the package to generate observations from the bivariate normal. But here using the metropolis algorithm, how do you generate the observations from the bivariate normal distribution? Incidentally, I must mention here that if we look at the proposal density or the jumping distribution, the jumping distribution is density, bivariate density, you can say bivariate normal, but the components are independent in the sense the diagonal elements. Bivariate normal with the variances are there, but the covariance between them is 0. So this is a more simpler situations, and generation from the jumping distribution is not difficult at all, because they are all independent univariate normal, right? So one can, using this code, can generate observations by following metropolis algorithm. Now, why does metropolis work? Keep in mind that you have chosen the Markov chain, right? So that the Markov chain has to be selected in such a manner such that this leads to the posterior density. So the sketch of the proof is like that. I am not going to give you the proof, but you need to show first of all that the simulated sequence theta 1, theta 2, this follows a Markov chain. Okay. The second thing is that show that the Markov chain has a unique stationary distribution, provided this aperiodicity and ergodicity, all these things, irreducibility occurs. So that this distribution, this stationary distribution, is actually the distribution of our interest, which is the target density. You can see the proof in the book, in the paper by Shiv and Greenberg in American Statistician 49 volume. Then comes the extension of metropolis algorithm. That extension has been done by Hastings, where he waived the fact that it should be symmetry. You see that these metropolis assume that the jumping distribution to be symmetry, and then Hastings waived this issue. that it does not need to be symmetric, and in that case the importance ratio change to, instead of only this p theta star given y by p theta t minus 1 given y, now it is changed to p theta star given y over j t, the jumping distribution of theta star given theta t minus 1, and p theta t minus 1 given y over the jumping distribution of theta t minus 1 given theta star. Properties of a good jumping rule. So, for any theta, it is easy to sample from these jumping distribution. So, you choose the jumping distribution in such a way that it is easy to sample from this jumping distribution. It is easy to calculate R, that depends on the target distribution. You see, the target distribution is already known to you apart from the constant. So, for theta star and theta t minus 1, you can compute this R theta star theta t minus 1. So, at any stage, at the pth stage, you can compute R very easily depending on the target distribution. Okay. Each jump goes a reasonable distance in the parameter space. Okay. This is called the good mixing property, and the jumps are not rejected too often. So, if the jumps are rejected too often, what will happen? Then you have a little chance to get observations for accepting your for fulfilling your purpose of getting the huge number of observations from the target density of interest. So, you make sure that it is not that too much observations are rejected. Okay. Ideal metropolis jumping kernel. Metropolis jumps in a normal setting. The jumping kernel should ideally have the same covariance structure as the target distribution, which can be approximately calculated based on the normal approximation at the mode. So, this is Metropolis Hastings, Metropolis algorithm, Metropolis Hastings algorithm, and then comes a little bit simpler approach, which is the gift sampler approach. The beauty of this approach is that here there is no point of considering any observation to be rejected or not. Every observation selected are accepted in the or included in the sample, because it has been constructed in such a manner that in terms of the Metropolis Hastings importance ratio, it makes sure that the probability of acceptance is always 1. So, you draw theta 1 from the gift sampler is that you look at the full conditional density. Suppose you have theta 1, theta 2, theta k are the parameters, and given the data, what you do, you consider the full conditional density theta 1 from theta 1 given theta 2, theta 3, theta k y, theta 2 from theta 2 given theta 1, theta 3, theta k y, and so on, theta k from theta k given theta 1, theta 2, theta k minus 1 y. So, this is how we generate observation. Each theta j t is sampled from the conditional distribution given all others. So, p theta j given theta minus j t minus 1 y. It means theta minus j means the theta vector consisting of all components except theta j. So, theta j, the conditional density of theta j given this are observations are generated from there. Okay. And then is theta j is updated conditional on the latest values of theta. Let us look at that, how this gift sampling ensures that all sample observations generated are accepted in terms of the Metropolis Hastings. You know that if we look at the importance ratio or acceptance ratio, you see that the jumping distribution is first of all the jumping distribution. The jumping distribution has been taken to be in our gift sampling approach p theta j star given theta minus j t minus 1 y if theta star minus j equal to theta minus j t minus 1. Okay. So, we in the jumping distribution has taken to be the full conditional density. Okay. So, the only possible jumps are the parameter vector theta star that match theta t minus 1 on all the components other than j. The ratio, then the importance ratio, if you write this thing following this jumping rule or jumping distribution, then you see that this importance ratio turns out to be 1. So, the chance that a sample is accepted is 1. So, with certainty every observation needs to be accepted. Okay. This is how it behaves. You see that, like, first of all, it takes the value somewhere here where you have the coordinate x1 and x2. I just show you just two parameters, say theta 1 and theta 2. So, for some value of theta 1 and theta 2, maybe the initial value, you start with that, and then there is a change from theta 2 to theta 2 1, but theta 1 remains same. Okay. Then there is a change in theta 1, theta 2 remains same. So, this way it goes on and on, that is how it goes. All right. Then like the previous situation, I show you three graphs where the observations are more and more generated. So, repeated observations generated, ultimately it gives you stationary the posterior density of or target density of interest. It forgets from where it started. You know that one other thing you must keep in mind, whether following the metropolis things or Gibbs sampling, that you must burn in first 50 or 100 observations for the sake of dependence, avoiding dependency, because the first few observations they have the dependence with the initial value. So, now later on it forgets from where it started. So, now if you delete first 50 or 100 or say 500 observations, then it gives you generated observations which forgets from where it started. There is no effect on the initial value. All right. Then this same bivariate normal distribution can be considered with the Gibbs sampling. Very simple setup. Code is very simple. You generate theta 1 given theta 2 and then theta 2 given theta 1 data. So, this is the bivariate situation. You have full conditional density you have generated. Okay. And it is very easy to generate from the univariate normal distribution, theta 1 given theta 2, similarly theta 2 given theta 1. So, one can get immediately write down the code immediately and get the things done. The burning questions that I was talking about is that earlier iterations are not representative of the target distribution influenced by the starting value. Okay. So, let us just look at the convergence, that how it goes. See, the more observations are coming, the more. See, you do not know that where the observations have been started from. Ultimately, it gives you a stationary behavior, and the stationary distribution turns out to be target density of interest or the posterior distribution of interest. Think of the rat example. Where earlier I have talked about the Gelfand also in his paper in 1990 considered this rat example, where the different rats, 30 rats are considered in different days, on different days. So, 8th day, 15th day, 22nd day, 29th day, 36th day. So, then the weight of the rats are taken, and Xij denotes, the 8th day means 8 days old actually, 15 days old like this. So, this denotes the age, and then you go for sampling distribution. You make a model like this, that Yij follows normal with alpha I plus beta I xj. So, this Yij weight, it depends on the age, how many days old the rat is. So, this is how the model has been framed for 30 rats, I equal to 1 to k and j equal to 1 to m, and for 5 subsequent days observed. Okay. Then these parameters alpha I, beta I are unknown, sigma square is also unknown. So, one can assume prior for alpha I, because it is a normal distribution, alpha I, beta I, acts as a conjugate prior, conjugate normal distribution, and say then again the hyperparameters are there, alpha naught and beta naught, which is not known, and then sigma. Then we consider the prior for sigma square again, inverse gamma, and prior for alpha naught, beta naught. So this is the third stage prior, level 2 prior, level 3 prior, and alpha naught, beta naught follows normal eta naught, eta 1, and C. So we assume that sigma inverse, this sigma inverse follows Wishart distribution with certain parameters like this, and the expectation of sigma inverse equal to R inverse, variance of sigma inverse is proportional to rho inverse. We seek the marginal posterior distribution for alpha naught, beta naught given the observed data, and predictive intervals for the individual future growth given the first week measurement. The number of unknown parameters is 66. So many parameters. This is the high dimensional problem that is created. 30 alpha i's, 30 beta i's, alpha naught, beta naught, sigma square, and 3 unique components of sigma square will lead to 66 parameters. So you have the model with yi follows normal, xi, theta I, sigma square in, and yi is yi1, yi2, yi ni. So accordingly xi and theta I is written, and then one can go for the Gibbs sampling, writing down the full conditional distribution. Theta I given y and other parameters follows normal with this. Theta not given this, that again follows normal with v and this. The expressions for v, for di, all these things are given at the bottom, and then sigma inverse has the distribution. So this is the posterior distribution of theta I, theta naught, sigma inverse, sigma square. This is normal, normal, Wishart, inverse gamma, all right. And then we consider the Weinberg. We apply this in Weinberg to ultimately get the posterior of thousands or maybe 10,000 or maybe 1 lakh observations on theta I, theta naught, sigma inverse, and sigma square, and then we compute the marginal mean that gives me marginal posterior mean for theta I, marginal posterior mean for theta naught, sigma inverse, and sigma square. So one can get separately for each column based on the generated observations the marginal mean, marginal variance, marginal covariance, all these things can be computed, and accordingly the inference can be drawn. One can also compute the credible interval or go for the testing problem or model selection problem in this connection. All right. So you might be happy to see that the Bayesian computing technique is a very path-breaking work in the field of statistics. What we studied so far, what we came to know so far, is that the Monte Carlo Markov chain, it's the use of a Markov chain technique where the Monte Carlo integration has to be done, that ultimately converges to the posterior distribution of interest. And people first of all followed the Metropolis algorithm, then they extended this Metropolis-Hastings algorithm, and then finally the Gibbs sampling algorithm to ultimately get the posterior distributions depending on the different situations. Usually, as I said, that in many situations the posterior distributions are not very easily tractable. In that case, the Metropolis-Hastings algorithm is the best choice, and we tried to illustrate that through a couple of situations and then showed that the algorithm, how it works, how it goes to the stationary distribution, the posterior distribution of interest. The Gibbs sampling is comparatively much easier to deal with, because there is no point of there is no question rather of rejecting any sample observations generated. But in the case of Metropolis-Hastings algorithm, there is a chance that quite a lot of chance that samples generated are not all selected in the sample setup. So this is the difference between the Gibbs sampling and Metropolis Hastings algorithm. Depending on the situations, we are going to use the Metropolis Hastings algorithm or the Gibbs sampling. All right.